we were discussing about, you take a sit. We were discussing about BOD modeling in static water. Remember yesterday, if I have not mentioned, say this has to be, this is in a BOD modeling in static water. We will continue this discussion. We will continue this discussion today also, and we will further move on to in the next class or so. We will move on to where is a moving water. So at present we are at BOD modeling in static water. Remember this, whatever we have discussed yesterday is basically relates to BOD modeling in static water. Those of you who could not hear this lecture, and please read them in this in the video course as such. So this is we have lastly we have found out that this is, we have also found out a relationship whereby we have said that L0 e to the power L0 1 minus e to the power minus kt, e to the power 1 minus kt, which shows that this is the this is what is the BOD t, the BOD remaining, BOD t, BOD remaining at or after time t, and this is what is this L0 we have already explained as ultimate carbonaceous oxygen demand, biochemical oxygen demand, and this one is 1 minus e to the power minus kt, where k is known as the reaction rate constant. Reaction rate constant is generally in the form of the unit that we have seen is would be day inverse or year inverse, or say hour inverse, like this. This is how the unit should be in the inverse of time, So here you can see this. So depending on that, the t would also change, essentially would also change, and so what you find is a basically a unit dimensionless parameter k into t, which is essentially reduces e into e to the power minus kt, and also so is basically reduces this, and so as a result of this there would be L0 would be LT would be the BOD modeling, we can very well find out like this. So having said all this, we can now find out that what is the importance of k, importance of k. If you observe in this function, when we began first is that dLt by dt is equal to minus k LT. This where from we have actually derived this LT is equal to L0 into multiplied by 1 minus e to the power minus kt. One we can see here is this k essentially, other things remaining same, other things like the quantity of the waste, other things like quantity of the waste remaining same, how LT or how this BODT, how LT or BODT would remain. So this is, I think we make a correction here. This is BODT, right? This is BODT. Please make a correction. BODT is equal to LT L0 minus 1 minus e to the power minus kt. That is what BOD, and this is LT is that the remaining the quantity of the oxygen demand left at the end of, so at the end of the time t. So here remaining same, how the LT or BODT will change. So here you see this quantity of the waste, if it is quantity of the waste is same, this would show a nature of this function would essentially be guided by this parameter k. Okay. So whenever, even if a waste is actually starting from, even if a waste is actually starting from a even if the waste is starting from, say, BOD, the same waste, even if that that it would have different values, would basically because of K1, K2, K3, K4. Okay, this is what is BOD remaining. So this is LT, then is and time, right? So how this function would be influenced, LT would be largely be guided by the parameter K1, parameter K, which is known as the reaction rate constant, This particularly, if you just trying to observe it experimentally, it has been observed that this K can be written as K20 into theta t minus 20, where this K20 is the reaction rate coefficient, reaction rate constant at T is equal to 20 degree centigrade. Theta is a constant, theta is a temperature coefficient, theta is known as the temperature coefficient, and which is known to be equal to 1.047, and this one is T here is the temperature at which this K is being measured. So you can see this KT, if you can write KT here, this KT is equal to T is the temperature in degree centigrade. Says degree centigrade. So you can find out. So here in most cases, suppose if you are given the value, of say K20 is given to you, you can find out KT, when you know theta is known to you, and also this the temperature, say temperature is at temperature, say T is given, say at say 35 degree centigrade or 35 degree centigrade, like this would be, this you can find out. One important thing that one can be seen here is, having said 1.047, so you can see now this one is essentially reduces to 1.047 into say a certain value, which is not a certain value, say more than say 35 minus 25, say here in such cases you can see this one is 15. So 15. So you can find out that with increasing temperature, the reaction rate coefficient also increases. I was telling you other day that with this means that more and more oxygen would be consumed as the temperature increases. As the temperature increases, more and more oxygen would be consumed. As a result of this, we can find out for different kind of wastes particularly. This is a general function. I mean, as I have said, for any kind of typical waste at two different temperatures, a higher temperature would show higher reaction rate, and the lower temperature would show lower reaction rate. All right. Now, having said this far, you can now find out that this one, then this one is, we can find out K20 of some of the wastes that is already experimentally known. This is K day inverse. We can say raw sewage. Raw sewage, it would be about 0.35 to 0.70. Then well treated sewage, well treated sewage 0.10 to 0.25. That is, here as his remarks, if you just put here remarks, say this waste load is decreased. Waste load is decreased from the earlier raw sewage. Okay, so this is polluted, say polluted river water. Polluted river water, we can find this value at between 0.10 to 0.25. Again, this value, this is polluted river water. In cases, say particularly low organic waste, this value can further be, sometimes it can be as low as, say, 0.03 to say between 1. So you can see this a wide range. If it is a low organic waste, if it's a low organic waste, particularly in many cases, say a mining waste is basically whatever is discharged is basically very low organic waste, or say in various industries like civil industry, you suppose road construction, or say building dams, wherever they are discharging some of the pollutants to the stream, it will mostly be characterized by low organic waste. It will be low organic waste, but there may be higher inorganic waste, but it should be generally low organic waste. In such cases, the depletion of oxygen, if you observe this depletion of oxygen, the rate is very slow, the very slow rate. So you can see, the slow means, if you are measuring oxygen, suppose you have started with the measuring of, as soon as it is meeting the stream, at the point of the meeting of the stream, if you take a sample at that point, and if you observe the oxygen, and you observe the oxygen in 3 days, 4 days, 5 days like this, you will see that the rate of depletion of oxygen is very slow. That is, if in the first day you find 10 milligram per liter in the oxygen level, you are likely to get, say, about in 5 days time you might as much as get 9.5 or 9.6 like this, or even at best 9. So this is how very slowly the oxygen would be depleted in low organic waste. Remember this, low organic and low biodegradable waste. I have also characterized that not all organic substances are biodegradable. There are many organic substances like ethers are almost completely non-biodegradable in nature. There are many substances. So this would also include non-biodegradable organic waste. All right. So here, this one you can see this. This is what we can observe that K20 as this. So whenever a particular temperature is given, try to modify the K20 into find out KT, and then use that, equate that function to find out, say, the BOD remaining, or say, as we have said, L0 is equal to LT plus L0 into e to the power minus kt. So here we would find out that LT, we just, I mean, just to recuperate, recapitulate the whatever we have learned, L0 e to the power minus kt, and that is how we found out that is, is it's okay, just 1 minute. L0 LT, it should be like this only. What I want, LT is equal to, this is wrong. We have LT, we have found out LT is equal to e to the power minus kt. This LT plus L0 would be BODT plus LT. So this LT, if you just put that, so BODT is L0 minus L0 into e to the power minus kt. So this, so if you can write it like this, so here we can find it like this here, that BODT is equal to L0 minus L0 e to the power minus kt, that we have already known. So L0 common, taking L0 as common, so is we find out a to the kt. So BOD remaining at time t would be essentially ultimate carbonaceous oxygen demand multiplied by 1 minus e to the power minus kt. So we have derived that only just to recapitulate in the from the yesterday's class. Okay, this is one thing. This is what we have learned so far. So this is how the reaction rate, and the reaction rate, how the calculation of the reaction rate would be done, is generally can be shown like this. Then there is another important aspect, is called the nitrification. It's a nitrification. The word nitrification here, this particular part of nitrification is one important thing. As I have said, if you remember, if I have said that this first 5 days are basically as I have said, about first 5 days there is no no decomposition of nitrogenous compounds, but as such, as we see, if after that this is the nitrogenous oxygen demand actually begins to increase. This is NBOD, this is CBOD, and this is total BOD. This will be total BOD. This is generally what I have said. If you just remember once again, that is, this is BOD, this is BOD, so this is BOD. Right, what I have said in that class is that till about 5 days is generally observed that the amino acids which form mostly the tissues of the body. Tissues of the bodies are generally formed of amino acids. These amino acids do not decompose for about 5 days. Till that time, we only find the decomposition of carbonaceous biochemical oxygen demand. That means carbonaceous biochemical oxygen demand, mostly you can write it like this. One representative, this thing is CBOD, would be mostly this. When we can in a NBOD, this is CBOD. The NBOD, what we find in NBOD is essentially CHNO, right? And say O is O. Then there may be some other substances like chlorine and all this thing. This can be phosphorus. All this can be linked, and we can find out NBOD as mostly all these things are C1, N1, HN2, N3, like this. So you can find out this is NBODs. The complexes, organic complexes, which have a nitrogen component, Now interestingly, this has to be found out that nitrogen is not freely available in water. Just say nitrogen is available, nitrogen in water is available only in ammoniacal form. So ammoniacal form, this is basically as an NH4 plus radical. Yes, right, NH4 ammoniacal form in an NH4 plus radical. This is what, this is what is NH4, but when NH4 begins to decompose, this NH4 begins to decompose. When NH4 begins to decompose, what happens is, the first thing, there are two bacteria at two different stages essentially carries this. One is called Nitrosomonas. This is helps in the first stage of oxidation, right? So remember, we are talking about NBOD. Here. So Nitrosomonas is the first stage of oxidation, and then the Nitrobacter. This is the second stage of oxidation. Nitrosomonas and Nitrobacter. These are the microbial group, essentially the bacteria. It's basically a family of bacteria. It's not a single species. Remember this, family of bacteria. These are the families of bacteria. These two kind of bacteria essentially convert the nitrogen, nitrogen locked as ammonia, to decompose into nitrate. Let me write down this equation here. NH3, let us consider this to be deionized 3O2 converted by Nitrosomonas essentially in most cases in the presence of sunlight, plus other natural enzymes. Sunlight plus other natural enzymes which actually spark the reaction. They provide the energy of the reaction. Most cases, many cases the energy of the reaction is very important. Unless and otherwise, the reactions would essentially not take place. So there should be a source of energy. So that source of energy is basically from sunlight or any other natural enzymes, or due to say the latent energy obtained from the water body itself. Okay. So here this particularly thing, this can be particularly, this is what we see is 2, sorry. Okay, let me take off all this. Where is this happening? It does not go off. Okay, anyway, let me start here. So here, as you can see this, so here as we have been explaining this reaction, let me write it again. So here this one is 2NH3 plus 3O2. This one is nitrosomonas. Nitrosomonas forms 2NO2 minus plus 2H. This is hydrogen ion released 2H2O. This is one stage. You can see this is called this is the nitrite, formation of nitrite. This is one stage of oxidation. This is one stage of oxidation that is taking place. The second stage of oxidation that takes place is converting this NO2 minus plus O2 into a nitrobacter. This is 2NO3. If you just add these two reactions, you can see this. This one cancels here. So another thing that is finally being produced is, if you can just see, 2NH3 plus 4O2 converting into 2H plus 2H2O plus 2NO3. Is that right? Okay, so you can very well 2 you can cancel it out. This is essentially, it forms a. So this is what is this. This is how this, and this is how this. This is what is nitrate ion. So this is particularly this nitrate is now amenable for acceptance. I say that it can be in the form of a solution in water. It would be mostly in the form of a solution in water. This would be available. So here there is here it is just a part of the famous nitrogen cycle. That is what we generally know of the nitrogen cycle. Just let me take a little bit on this. The partly what happens is, this is how the mechanism actually takes place. This is how the mechanism essentially takes place. This is the plants. This is plants, the animals, then from the animals coming the organic nitrogen, death, excreta, etc. So you can see here, these are possibility of two sources. One is the biochemical sources. There may be some biological sources also, some with or without biological sources, okay, some biological sources. This is essentially a biochemical source. You can see death, animals by death, supplying organic nitrogen. Excreta is also supplying organic nitrogen. So here this is what is, the plants are also contributing by different types of leaves dropping, death. Alright, this particularly would be, then we find out ammonia. This is what is essentially what is generally being converted as such, is amenable. At the same time, as I have said, after about 5 days of decomposition, you find NH3 this NH3 would be finally formed as nitrate, nitrite, then it is nitrate. There would be some kind of nitrogen in this. This is denitrification. So you can see this is the simplified biochemical cycle of nitrogen. This is biochemical cycle of nitrogen. All right. So let me explain this. Plants and animals, by their leaves dropping, death and all this thing, the death, excreta, then other means of decomposition, whatever other means of decomposition. This supplying organic nitrogen. This is organic nitrogen, as I have said, would be bonded, CHNO, phosphorus, P. All this in a particular bondage, which would be available for oxidation at about 5th day, that I have said. At about 5th day, when it is available in the form of ammonia. This ammonia can be directly some of this ammonia can be directly taken by the plants, and the other most of the ammonia would be first converted into a nitrite and then into a nitrate. And this, from this nitrate also it can form N2 and N2O, or otherwise this would finally go for, after a fixation, would go to the plant. Say there are leguminous plants which can fix nitrogen in their plant roots, and this should be fixated in the plants, and then finally this one is when it is by lightning. You just write this. This is lightning, this particular N2, N2O which is released from this NO2, one of them would be in the atmosphere. This is all in the atmosphere, due to lightning may be fixated as nitrite, and this nitrite, whenever coming out in the rain, coming in on the ground with the rain, they may be again absorbed and can be turned back, can be absorbed by the plants. So the nitrogen, one part of the nitrogen cycle is that by which by the decomposition, by the leaves dropping, or say by other biological sources, these biological sources where nitrogen would be generally supplied. This is one source of nitrogen coming in. Another source of nitrogen is from this nitrogen, whichever is getting released in the atmosphere. Some of them, due to lightning, particularly during this the rainy season, most of the nitrogen in the upper atmosphere would be would react, because there would be energy of reaction for nitrogen, which would convert it to nitrate ion. This nitrate, this nitrate and this nitrate would essentially be used by the plants for the fixation and for the fixation to develop amino acids. Amino acids are mostly, these amino acids would be used by the plants, and their formation of tissues, formation of say cellulose, these cellulose structures, all this would be formed by this nitrogen. So nitrogen is an essential element for tissue formations. So tissue formation, so these tissues and all this plant tissues and the plant related things would be essentially supplied from two sources. One is the atmospheric nitrogen getting converted into nitrate, and the biochemical nitrogen converted into nitrate and then being adsorbed. This is a typical nitrogen cycle that we know of. So here, say this is particularly, have you see there are the way we generally find out how this nitrogenous oxygen demand, nitrogenous oxygen demand. So in the nitrogenous oxygen demand, we generally try to find out, as you have seen, if you have seen this last reaction, in the last reaction you can see this one is here, the oxygen is being used. What is the demand of oxygen? What is the demand of oxygen? That can be found out. Nitrogenous of a waste, the same can be found out, but certainly with certain assumptions. I mean, I will explain you how these assumptions take place, but you can see physically the oxygen would be consumed. This oxygen would be supplied from the water. Remember this. This oxygen would be mostly supplied from the water. So not only CBOD, but NBOD is also taking oxygen from the water. So this should be, this particularly, when you see this particularly this nitrogen oxygen demand, we generally is say what we generally find out, the essential important thing that is one typical reaction that we generally use of is that NH3, that is that we have found out is that 2O2 is equal to NO3 plus H plus H2O. If you remember in the last case, so this is nothing but if you just take out this one into 2 and 2, 2, 2. This is the typical reaction that we have just found out. By which nitrosomonas and nitrobacter convert ammoniacal nitrogen into nitrate. The same where you can see this here, only you can very well find out that this is, this is one relationship, but you can sometime remember this is one relationship, but this not necessarily only relationship. This is not necessarily the only relationship. There can be other substances of nitrogen, say if we find out other say as a function of CNH, any reactant, any available substances which are readily oxidizable combining with nitrogen. In such cases, you see this one is, if we can establish XO2 into say NO3, say this is YNO3, then ZH plus XYZ, say MH2O. If you can establish a relationship, we can also find out we can also find out, say, the oxygen demand. We can also find out the oxygen demand. It says, this is, try to understand this. This is a basic equation that we have just found out, right? How this Nitrosomonas and Nitrobacter uses. But this is not necessarily the only relationship, only function, only reaction explaining how the nitrogen in the water would be converted. Nitrogen may be locked up in any different forms also, which is possible that they also would be oxidizable. They are oxidizable, and when they oxidize, they might form these substances as well. So if we know this, if we know the characterization of this CNH, this function, plus if we know that X, how much of X is required, we can always derive what would be the reactants, what would be the products of the reaction, what would be the products of the reaction. So having known that, we can also find out the typically the relationship. So here you can see here one thing for this relationship here, if we taking 1, we can see that 17 gram, this is in terms of 17 gram of 17 gram of ammonia, 17 gram of NH3 plus this 2 into 32, that is 2 into 32 oxygen would give rise to see this NH3, this 14 gram of this is will give rise to 14 gram, not 14 gram actually. It says this is what it is producing, this reaction is being produced. So here you can see this H plus, this is in an ionized form, so not necessary that we write this reaction here. So NBOD can be very well say if the milligram of the waste is given. So nitrogenous waste, now say for example, say nitrogenous waste concentration is nitrogenous waste concentration is say 40 milligram per liter, right? We have identified that in the waste. We have find out that whether the nitrogenous waste, we have found out carbonaceous waste, we have found out nitrogenous waste, and we found out that the nitrogenous waste concentration is 40 milligrams per liter. If it is 40 milligrams per liter, NBOD can be found out as 40 milligram per liter multiplied by 17 gram. For every 17 gram of NH3, that would be formed from this 14 gram of nitrogen, multiplied by 64. So here, so you can see this 17 gram, it is 17 gram of NH3 would require 64 gram of oxygen, 64 gram of oxygen. So 17 gram means it would be basically 14 gram of nitrogen. For every nitrogen, this is for every gram of nitrogen, this one is 17 gram of NH3. For every 17 gram of NH3, for 17 gram of NH3 we would require 64 gram of oxygen. This multiplied, every 17 gram of NH3 would essentially form 14 gram of nitrogen. So here we can see this nitrogenous biochemical oxygen demand that we found out to be how much it should be. Say it is about say how much it is coming out. Can you find it out for me? So this one cancels out. So 40 into 64. This is 640 into 4. There is 286. 256. The sheer 256. Okay, 250 divided by 14. So it is basically 40 into 64 divided by 14, isn't it? 170. Okay, it's a 170 milligram oxygen per liter, right? This is because this is the waste that we have said is 40 milligram. This is the unit. This grams are getting cancelled, only this milligram per liter remaining. So you can see this would be finally in the form of 170 milligram per liter. What we are finding out is, here is just case, if you just see this equation here, for 40 milligram per liter, what we are say, for every 17 milligram of nitrogen would provide 14 gram of, for 17 gram of ammonia would provide 14 gram of nitrogen. That is clear. That is for 14 gram of nitrogen. If it is convert into free nitrogen, so this 14 gram of nitrogen it should produce. And say for every 64 gram of oxygen, this 17 gram of nitrogen would use 64 gram of oxygen. So this one is, that is how we are finding out for every nitrogen, for every gram of nitrogen, what would be the requirement of requirement in case of the requirement, the amount that would be required is 170 milligram of oxygen per liter would be generally known. This is what is how this we generally found out this NBOD. Remember one thing, if in some cases if you find that this reaction has been changed, the reaction has been changed, so in such cases you also have to automatically change the molar value has to be found out. From the molar value you can change the parameters for calculation. Is that clear? Okay. Now this particularly, this is the value that you generally get is the oxygen demand, say the oxygen demand due to nitrification, divided by the concentration of nitrogen, concentration of is 170 milligram, say milligram of O2 per liter divided by say 40 milligram per milligram nitrogen per liter. So this one is, we find out for, we would require for 5.57 milligram of oxygen per every milligram of nitrogen present in the water. This is known as, this 4.57 is known as, so ultimate, this is known as total Kjeldahl nitrogen, this is TKN. So this is known as this, the total concentration of organic and ammonia nitrogen so NBOD toward this ultimate NBOD, ultimate NBOD would be generally known as, if this is say about 4.57 into total Kjeldahl nitrogen, TKN. This is total concentration of organic and ammoniacal nitrogen. Ammoniacal nitrogen is known as total Kjeldahl nitrogen. See, this total concentration of organic and ammoniacal nitrogen. Organic and ammoniacal nitrogen is a total, this is known as the TKN. This is what is, this is total TKN. This is total Kjeldahl nitrogen. This is what is TKN. For every, for say for every gram of, or for every gram of milligram per liter of organic nitrogen, for every milligram per liter of organic. So you can see this, for example, ultimate NBOD is 4.57 milligram of O2 per milligram of nitrogen. This TKN, if this TKN is generally say if we find out say 50 milligram per liter, this 50 milligram per liter, then you can see this, about 4 is, say total is 4.5, so it is 4.6, say 4.6 into 50, 4.6 into 50 is 230, right? 230, about 230 milligram of oxygen per liter. milligram of oxygen per liter would be required. So the ultimate in NBOD can be found out like this. Is it clear? Okay, if it is not, I mean, you can always read it again, see it again. If it is not, we can again discuss in the next class. But till that time, this part is almost complete. So we'll move over to the stream BOD, or this is so far is the fixed and still water. So we'll move into the stream now, from, if there is no other question to discuss. Okay, all right. We stop the class now, and this is where today's class would be stopped. So we will move over to the next class with the stream BOD.